There it goes. Okay, so simple harmonic motion. Before we actually delve into and define it, I'm going to remind you of what we talked about right at the very end of class right before Thanksgiving break. We did a little lab. Do you remember the little lab that we did with springs?
Oh, yeah.
And we put masses on them? And we defined this whole law that we didn't really talk a whole lot. I mean, we talked about it. And the reason I threw it into that section was because it's important for the energy of springs, because we were talking about energy, and so it kind of made sense to put it in there. But they actually go through Hooke's law in this chapter. So if you were kind of like, oh, that was kind of weird before, now you could take a look in there. I just want to remind you of a couple of things about Hooke's law, or have you remind me of a couple of things about Hooke's law before we get too far into other stuff. So, it's been a little while, a couple weeks since we did this. What did we do in order to establish this law that Robert Hooke had established a few years before? What was the process? What did we do in that lab? You had a spring. You had some masses. What'd you do? Did you throw them at each other?
We kept adding masses on the spring and measuring the spring's displacement from equilibrium.
Okay, let's have one conversation. What happened?
We kept putting more and more mass on the spring and each time measuring the spring's displacement from equilibrium.
Does that sound familiar to you? Yeah. So you were putting masses on the spring and then you were measuring the displacement from equilibrium, and you graphed it too, didn't you? And when you graphed it, we had a long conversation about what you might graph, but one of the options was to graph the force of gravity, which we might argue, I think we drew this picture before, but let's just remind ourselves here, that we have the force of the earth acting, right? And the force of the spring. And how did those two forces compare? Come on, friends. You got to know this stuff. How did those forces compare? If you need to analyze it, there's a spring hanging off of my desk up here. You can take a look at it. There's a mass on that spring. Same forces are acting as those forces there.
They're equal?
How do you know they're equal, Chris?
Because it's not accelerating.
Yeah. Does that make sense? Okay. This is one of those fundamental things, my friends, that we really, really need to make sure is ingrained in our brain. Okay? You don't need to remember the little minutiae necessarily, but that would be a fundamental thing that you need to know, regardless of however many days you've been sleeping in until 3, and so you actually shouldn't be up yet. Okay, and then you just consume pie for the remaining 2 hours that you're awake, and then you go back to sleep. I don't care. Even in that pie coma state, you still should be able to tell me that the two forces acting on that mass right there are equal in magnitude, right? Because we've been talking about that for about ever. And we know that those have to add up to 0 because it's not accelerating. Is that okay with everybody? Every day that's true. So if I graph the force of the spring here, and then, Justin, you said we put mass here? Yeah, we put the mass. Well, actually, the mass goes over here, right? That was because the force of the spring is equal in magnitude the force of gravity, which is equal to m times g. So really, the mass is hanging here, hanging out over here. What can we put over here? What would be an interesting thing? What did you put on this axis? Or what could you put on this axis?
Oh, the displacement.
The displacement? The displacement? If we mark that maybe with an X. And when you graph those two things, what do you get? What does it look like?
Line.
It's a line, right? It is. It's a line. Something like this. Wasn't it? And being those clever physicists that we are, knowing that it's a line, again, that equals y equals mx plus b, because we can always come back to that. What would we plug in instead of our y? F of s, the force of the spring. What are we going to plug in for b? Take a look at our line. What's b?
0.
0. We want it to be 0, right? We're going to try and force it to go through 0. It should be 0. And what's our x? Perhaps a trick question.
It stays the same.
It's x, right? X is the displacement. And then you have m. And m is the slope. And we decided that the slope is what we're going to call the... The spring constant. We mark that with the letter what? K. I really hope that you're all still just in your food coma and that you know this and you're just not speaking. Because if you don't know this, then you need to go back and look at this stuff, okay? This is information that you should know, that even though you just took a test over it, and then you left it, like it left your brain, it still should be back there somewhere. And as we talk this through, this should still live there. You should be able to tell me this stuff. There was a negative sign in there that we didn't really talk about last time, but I want to throw that out because it is important now. There's a negative sign that lives there. I want you to take a look at that. I want you to think it through. And I want you to see if in your brain you can explain why there should be a negative sign there. I want you to think that through right now. Why should there be a negative sign? What does that negative sign mean? Talk to your neighbors. What does that negative sign mean? Why?
The negative sign means that the force is always going to be opposite the displacement of the spring, right? The principal harmonic motion does this. So it's never, that's really loud. So that's what makes it harmonic. Just going to keep going back and forth until it goes like. A negative sign is what makes it safe and bounds.
Why is it negative? Why is it negative? David Wheeler, did you guys come up with an answer back there? A guess even?
The displacement's negative.
What do you mean the displacement's negative?
I don't know, from like where the spring starts to where it stretches to.
So like here's where it was, is that what you kind of mean? Sorry, you're like, I can't see what you're doing. Here, let me pick it up so you can see it better. So it was here and now it's going down, is that what you mean?
Yeah.
That the displacement is negative? What do you guys think? Does that make sense? I agree with that statement. I think there's a little bit more that can go with it also. Seth, you look like you want to say something.
No, I was thinking just trying to, I don't know what you're going to add onto it.
Chris?
Is the force of the spring equal to mg?
The magnitude of the force of the spring, like this thing here, is this what you're asking me?
Yeah.
Yes, I would agree with that. The magnitudes are.
So since gravity's negative,
Okay.
then you have to put the negative on the other side too to keep the force.
Did you mean to say work like work or like
No, like equal.
make it okay?
Yeah.
Okay. So yeah. So which way is the force of the spring? Which way is the spring pulling?
Upwards.
In the positive direction, the upwards direction. Which way did the displacement happen?
In the downward direction.
In the downward direction. Does that make sense? So the force, which is a what? What's that thing mean?
Vector.
It's a vector. and the displacement, which is also a vector, will they ever point in the same direction? So this is the thing. The lab that we did before was just to look at this thing and let it sit here, right? That was kind of unexciting. Today what we're going to do is to let this thing bounce up and down and up and down and up and down and up and down. Oh, that's fun. Good thing you came back today, right? That's good stuff. It goes up and down and up and down and up and down. As it's going down, the further down it goes, the more force it's going to feel in the what direction? In the positive, in the upward direction. Now, what about, so this spot here we could call equilibrium. Have we used that word yet?
I don't think you
Officially?
Not officially.
Not officially. But you're kind of like, I kind of get it back there. What does equilibrium mean?
When there's no force acting on the spring.
When there's no force acting on the
On the
mass.
mass?
Yeah, because the spring is the thing that's acting, right?
Oh, sure.
You know, I mean, we could talk about the forces on the spring, but then it would be like me and gravity, and that's not very exciting.
Okay.
So yeah. So let's write that word down, because that's not an unimportant. It is an important word, is what I'm trying to say. So let's write that word down. Equilibrium. I think it's one of those words that I intend to use a lot, and I just kind of forget sometimes to actually use the official word, because we talk about this idea of equilibrium all the time. David, you just said it, but say it one more time. What does it mean for something to be in equilibrium?
No forces are acting on the mass. Well,
No, what force is acting on the mass?
I don't know, like no net force.
Yeah. No net force. And so that super smart part of you can also say then, if there's no net force acting,
The mass is not accelerating.
there's no acceleration, right? That's Newton's first and second law, right? F net equals 0. That means what? Acceleration is 0. Yeah. I'm going to say object instead of mass to be a little bit more. So that's important too, okay? The object isn't accelerating, no net force is acting when this thing is in equilibrium. Now, what was the whole point of that? Oh, right. If I have this pulled down a little further, the further down I pull, the harder it's going to pull up, right? What if I let it go? Is it going to just go back to equilibrium and sit there?
It's going to go past equilibrium.
No. If I let go, so if equilibrium is like right here, and I pull this down, it's not just going to stop there. It's going to bounce up and down and up and down and up and down and up and down, right? Boinga, 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 boinga. It's fun. You are getting sleepy. Whoa. I won't do that very long because we all okay? But it's going to go past equilibrium, and then so it's going to be up here sometime at this point. Now, is the net force 0 now? When it's way up here past equilibrium? Is the net force 0? Oh, that's a good question. I don't know, Miss Carbeling. What do you think? Jordan, what do you think?
I think it isn't. I think that the force on the spring when it's way up there, the force on the spring has been greater than the force on the earth. That's why it went.
Okay.
So that's why it was accelerating upward.
Yeah. So what about now when it's way up here? Then is the net force
on-
0?
No, because the force on the earth is greater than the force of the spring.
Does that make sense? Okay, so at this point then it's not 0 either. It's going to fall back down because gravity's going to pull it down. Is that okay?
Yep.
Okay. So you got these two forces that are kind of playing against each other, trying to get this thing back to equilibrium, and it just keeps shooting over through and through and through and through. Question?
Yeah. If, of course, assuming that friction and air resistance are both negligible,
Yeah?
and you are somehow in an area with no gravitational forces acting upon the spring and the mass on it, would it keep going forever and ever?
Sure.
That's what I thought.
Yeah, you could even have gravity acting as long as there wasn't any air resistance and it was
confirming.
perfect.
I
Ideal spring, yeah.
I thought of the negative sign in a different way.
Okay.
Yeah, using an ideal spring.
Uh-huh. Yeah. So here's is that all you needed to say, or did you have
Yeah,
something
that's
else?
all I
Okay, okay. So that negative sign is like really crazy important. It's like got a whole thing that goes with just that negative sign. Let's talk about that crazy important negative sign. That negative sign means that this force is what we call a restoring force. A restoring force is one that tries to return a system to equilibrium. Tries to return a system to equilibrium. What's that, Mira?
Just a question about before. If the object is moving at a constant velocity, would that also be considered equilibrium?
Yes, as long as it's not accelerating.
Okay.
Yes, yes, absolutely. Yeah, so had I been thinking ahead, perhaps, in August, when we define Newton's first and second law, I should have just thrown that word in, right? Basically, Newton's first law, when something is not accelerating, any time that it's not accelerating, it's in equilibrium.
Okay.
It's not special to this unit. I just apparently hadn't used the word before. I don't know why. Just slipping up.
Yeah.
Slacking. Sorry. Yeah. Yeah. Okay. Life is okay so far? Okay. So, this is important. This thing gives us pretty much everything that we're going to do in chapter 16. Okay? That force, that idea of a restoring force, provides us with all of the information that we need for this thing that we call simple harmonic motion. Okay. An object in simple harmonic motion, or a system in simple harmonic motion, is defined as a system in which the net force is proportional to the displacement from equilibrium. Oh my goodness, why? Just needed a break for a second there. Come back. All right. Okay. Is that okay? I would like to know if you can think of anything else besides a mass on a spring that exhibits simple harmonic motion. So I'm going to give you a minute to think. Think about things where this might be true. Give you a minute. I want you to be creative. I don't want you to not write anything down. I want you to write something. Give it a shot. Can you come up with anything that exhibits this type of motion besides a mass on a spring? Think about it for a minute. Write anything down that you can think of. All right, creative thinkers, what did you come up with? Isabel, did you guys come up with anything?
But it doesn't spring.
I said something about it has springs.
Oh, you could. I just didn't want everybody to write this, right? So if you have other things that have springs, what did you get? What did you write down?
I wrote trampoline.
A trampoline. What do you guys think about a trampoline? Do you think that exhibits simple harmonic motion? Like, are you talking about a kid on a trampoline, or like just the trampoline itself?
Well, I don't know. Both.
Okay. Okay. What do you guys think? Do you agree?
That's what I have.
I think
That's what you had too?
Yeah.
Also, other people
I
are
think
having.
a kid on a trampoline
That's
counts
a person on a trampoline.
if you ignore air resistance.
Okay. What do you guys? What else? Other people? Swing set? Swing set, absolutely. I would say kid on a trampoline, not so much. The trampoline itself, like the reverberation that it has, I haven't jumped on a trampoline for ages, so I don't have a lot of firsthand experience with this recently. But I would say that part, yes, absolutely. Absolutely. The trampoline itself, like that tight thing, yes. Let me write this down. And what part of this, like it's just sitting there and it's simple harmonic motion? What about a swing set is simple harmonic motion? Or the swinging, yeah, like the kid in the swing, wee, absolutely. Yes, I would agree that that's some simple harmonic motion. I've talked to you a bunch already today. What?
Maybe if there was like, we weren't sure if this actually would work or not, but if there was like a teeter-totter and you had like two pretty equalish masses, and so you had one mass and it was sitting there kind of like this, but then you added the other mass, wouldn't they kind of go down but then like even out, maybe?
So if it was really like very little friction and so it was kind of like, I don't know, honestly. I mean, I think you would have to have a very, very well-oiled teeter-totter.
Yeah. And two very identical children.
Yes. It might. I'm not positive. So I can't say yes or no. I'd have to think about it a little bit.
Okay.
But I'm going to give you another example that may kind of help us to do that in a second. What other examples do you have? So maybe a teeter-totter. Is that how you spell teeter-totter? I don't really know.
Yeah.
That's
Sweet.
how I spelled it.
Okay.
Oh, seesaw, that's easier.
That works, yeah.
We would like dropping a bouncy ball and then it hits the ground and bounces up and bounces till it returns.
Without air resistance and friction. Without air resistance.
I don't think it's actually. Let me tell you why. And don't be upset. Don't be like, meh. Because there's something very. So it does exhibit some sort of like oscillating motion, right? And there's a difference between just oscillating motion and this very specific thing that is simple harmonic motion. So I'm glad that you brought it up because it's a fundamentally different deal. The deal here, because I'm thinking about with a bouncy ball, the net force isn't proportional to the displacement because, you know what I'm saying? Like it doesn't have a net force acting all the time that is proportional to displacement. The net force acting on the frog the whole time is the same, right? So it would be as if you have a bouncy ball, or I just don't have a bouncy ball with me, but my frog. It's as if the force of gravity changes as it gets closer. Do you know what I'm saying? So not quite. Now, there is something, so I said that, then I'm like, well, maybe not. Because technically, at a very fundamental level, the force of gravity does change. So there's a classic problem that we'll get to eventually, where one takes the Earth and cuts a hole all the way through the Earth, through the center, okay, to send a message to your friend over on the other side of the Earth, right? So you take a little message in a bottle and you put it down here, and what's going to happen to it as it falls? Does it feel a force? It feels a force, and that force varies as it gets closer and closer and closer to the Earth. That is true. And then it gets to where the equilibrium point is right here. But does it stop?
No.
No. What's that?
It still has the velocity.
What did you say?
I'm gonna say it burns, which is probably true.
Well, whatever. Mantle core, blah, blah, whatever. It's going to go through. Guys, stay with me, please. And it's going to slow down, right? And so the force is going to be dependent on the distance. But you have to be able to do this oscillating motion back and forth. So kind of yes, but not quite. Fair enough? So we'll say, yes, so we've got like a message. Through the Earth is actually simple harmonic motion. That's kind of weird. And that's kind of what I was thinking with yours too. It's, do you know what I'm saying? Like it's not, yeah. And then there's one more that I'm going to bring up in just a second, but I don't know what David's going to say. Will you guys be quiet so that I can hear? Thank you so much. Go.
I said like a wind-up toy,
Like the little
yeah, kind
walking
of,
things?
I was thinking more like the rubber bands. Like, I don't know if anyone was ever in Cub Scouts, but we made these airplanes that had rubber bands through it, and then you wind up the propeller, and then you let it go, and then the rubber bands would
Unwind?
and it should go forward. Yeah.
So I think also that would, it's kind of like my other response there. The thing that makes simple harmonic motion unique in and of itself is that you have to have something that's going through equilibrium, through that net force equals 0 place, and then it keeps going the other way. Do you know what I'm saying? So the fact that the rubber band unwinds gets you to equilibrium, and I don't know these airplanes exactly, but I'm kind of imagining what it would be. But it stops after it unwinds, right?
Okay, yeah,
Do you know what I mean? That would be the little difference.
Okay.
Yeah.
Yeah.
Go ahead. Oh, go Ellie, and then we'll go here. Yeah. Tell me more about what you're talking about. Yeah. Yes.
Would that work?
Yes. That would be. I think so. Yes, in that Jell-O has a spring constant that one could measure, right? You could measure the spring constant of Jell-O.
We should do that.
I don't know. I would need you guys to think about how to do that effectively.
If we can think of a good way, can we do that?
Sure. If you can figure out a good way to do it.
That could be an interesting lab.
But yeah, I think so.
Jello.
Maybe I need to say gelatin dessert so I'm not stealing some copyright laws. So Jell-O, what do I want to call it? Wiggling? Go.
Like a metronome?
A metronome? Do you guys know what a metronome is?
Yes.
Tick, 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 tick. Absolutely, that is another one. Metronome, is that how you spell it?
Yes.
I don't spell well. What?
And then how about pendulums?
How about a pendulum, right? A swing set, a kid on a swing, and a metronome are just examples of
Pendulums.
pendulums. You guys all know what a pendulum is. You've seen these, right? We did this lab in 9th grade, or in accelerated physics. You've seen it at the Science Center. You've ridden a swing. You have been a pendulum.
You have left off of it.
Okay? Are you kind of getting this idea of what's going on here?
Mhm.
Do you see the difference between the things that I said, yes, this is definitely one, and these, even though they're doing oscillations, or even though they're related to rubber bands, or even though they've got stretchiness going on, that doesn't necessarily mean that we've got this piece. That's the key, okay? There was one little bit that I forgot to add there that I want to make sure we add, so make sure you do it as well. For the definition of simple harmonic motion, a system in which the net force is proportional to displacement from equilibrium and there's an and in there, sorry. The net force is always directed toward the equilibrium. Okay. This definition is a very, very important one, so you might want to put a box around it or stars by it or glitter pen it up or whatever it is that you do to make sure that we know that this is important. Okay. Net force is proportional to displacement and is always directed toward the equilibrium. So far, so good? 3 more important words. Maybe you know the definitions to them. I'm going to give you the words. I'm going to let you write down some definitions. Here they come. Amplitude, period, and frequency. I'm going to give you just a moment to give some definitions. Write down something. What do you think they are? How are they measured? All right. Cora, I haven't talked to your table yet. I don't know. I just had to identify that I hadn't talked to you guys yet. Do you want to give me a definition for one of the words?
Alright, well, for amplitude, we have the height of the wave,
Height of the wave, and then what'd you say?
Like how high and how far below. The zero. So, like if the graph is instead of the x-axis, like, I don't know, but it doesn't necessarily do that. So.
Okay. Okay. Fair enough. What do you guys think? Do you agree?
Isn't the amplitude just from like x-axis to the top, like to the height, to the maximum height?
What do you guys think? Do you agree? Yeah. Yeah. Now, does it have to be a wave? So, like in this case with this little funny thing here, how can I find the amplitude of the oscillation?
This is how high it goes. Equal like the max.
Yeah.
So, how high it goes from where? From equilibrium. Is that okay?
Yeah.
So, I'm going to just adjust that a little bit, but you're exactly right. So, it's the height of the wave. That's a really good definition if you have a wave. But if you don't have a wave, then let's change it just a little bit to maybe say okay, I need words. Help me, friends. Maximum displacement. From what'd you say, Allison? Is that okay? And these really do mean the same thing, and we're going to kind of put it all together today. But I want to look at that kind of piece for something that's just oscillating up and down, because I don't yet see that wave part to it. What are the units that we're going to use to measure amplitude? Cora, what did you guys talk about for units? What units are you going to use?
We did not do units.
Do you have an educated guess now? Come on, ladies, you can do this. It's a height. What is it going to be measured in? Is it going to be measured in seconds? What's that? Centimeters would be an okay choice, but probably not the SI base unit. There. Okay, so I'm going to ask you for the next two also, so make sure you're ready, okay? Definition. Let's see, V, what did you guys say for period?
The amount of time it takes for a cycle to occur.
Amount of time that it takes, what did you say?
For a cycle to occur.
For a cycle to occur. Does that make sense? So, what do you mean in terms of this oscillation thing? What is a cycle? What does that mean technically then? How do I find the time? I don't disagree with this. I just want you to be a little more. I'm going to keep asking questions because that's my job. No.
Okay.
I mean,
Well,
if you don't have an answer, that's okay. I just wondered.
From the lowest point to the highest point, back to the lowest point.
Okay.
So,
Does that make sense? From one place all the way through and back. Absolutely. That's perfect. Yeah. And Ellie, what are the units going to be for period? Seconds. Because it's in a measure of what? Time. Yeah. I didn't actually put this for the other one. For amplitude, we're going to call that A. That's the letter we use for amplitude. What letter do we use for period?
P?
Not P. P is for power or momentum, right? We've got too many P's already. T. Capital T is for period. Capital T is for period. Because that's logical. I mean, it's like time, right? That's kind of what we think. All right. Hey, Taylor, what'd you guys say for frequency?
We said number of periods over a certain time.
The number of periods. What'd you say?
Over a certain time.
So I think I understand what you're getting at, but I'm going to do my poking thing because that's my job. So, do you mean like, well, first of all, what do you mean by periods here? Like the number of times? Like is it
Yeah, how many
a... So would you say how many?
cycles?
Cycles. I like that better. Yes. So I'm going to say the number of cycles. Is that okay?
Yeah.
I'm just being picky because that's my job. I get paid for this stuff. I want to earn my paycheck this week. All right. So the number of cycles over a given amount of time. So over a second or over an hour, over a year. It depends on what kind of thing you're measuring, right? How often does something happen? If we generally measure time in what units? Seconds. The unit for frequency is 1 over seconds. So sometimes you'll see it written like this, 1 over s. Sometimes you'll see it written as s to the negative 1. Or sometimes you'll see it written as hertz, Hz. Hz for hertz. These all mean exactly the same thing. They all mean exactly the same thing. The letter we use for frequency is? You can go with your gut because you were right this time. What is it? F. Yes. That's not supposed to be a fancy F. It's just a little f. I don't know why my F looked so fancy. There you go. It's a little f. Is this okay? Okay. I have a couple questions that I want you to answer. They're quick quiz questions from a textbook that I have that you guys don't use. They're not super easy to read because I didn't get them retyped. So I'm going to put them up and turn the lights off so you can see them a little bit better. And then I'll read you the pieces that are hard to see in here as well. Okay? I need to retype them. I just haven't gotten my act together. So I apologize. I'll make them a little bit bigger and then we'll come to that third one in a minute. So they're multiple choice questions. So I want you to do them by yourself first and then we'll discuss all 3 of them at the end, okay? So the first one says, a block on the end of a spring is pulled to a position A and released. Through what total distance does it travel in one full cycle? The choices are A over 2, A, 2A, and 4A. I'll let you think about that one, write down an answer, and then... Can you guys read those, or do you want me to read them to you? Can you see them from way back there?
Yeah.
Oh, okay. Okay, I won't read them to you then. I'll just give you a minute to take a look. Oh no. Has everybody finished 13.1 at least? Can I move this down to 13.3 or 13.6? I lied. All right. So I'm just gonna look. I just want to see maybe where we're at. I'll make a little chart here just so we can. So put your boards up. Let's see what we got. So for number 1, we have 1, 2, 3, 4. You want to hold your board up for me, yo? Got a bunch of D's and a C. Let's take a look at number 1. Woo! Somebody want to defend their answer for number 1? Why did you say what you said? Go. Yeah, Allison, go for it. make sense? 1, 2, 3, 4. 4. It should be D. Yes. Good job. Good show. All right. Number 2. What did you say for number 2? I didn't actually look before, so let me look now. All right, let's take a look here. For simple harmonic oscillator, which pairs of vector quantities cannot be in the same direction? Position and velocity, velocity and acceleration, position and acceleration. Defend your answer to me, please. Go, Jordan.
It has to be position and acceleration because no matter what, where the position is from equilibrium, the acceleration has to be pulling it back towards equilibrium. So like if it's in a positive displacement from equilibrium, saying that like upwards is positive.
Okay.
If it's in an upwards displacement, then it's going to be accelerating negatively back towards equilibrium, and if it's in a negative position, then it has to have an acceleration that's pulling it back towards equilibrium.
Okay, so if we go back to the definition, right? I'm just pulling us right back. The net force is proportional to the displacement and is always toward the equilibrium. So that displacement is always away from the equilibrium, right? And the net force is always pulling back toward it. So we could use the argument. I'm just going to come back over here. If you say F equals negative kx, and that equals ma, is everybody okay with that? And we put little vector hats on all those things, and we ignore that this one even exists. This negative sign means that these two, because K and M don't have direction, X and A have to be pointing in opposite directions. All right, are we doing okay so far? One more? Let's see what you said for that one because I don't remember. Okay, a little more dissension. All right, here we go. We got to discuss this one too. The amplitude of the system. The amplitude of the system moving in simple harmonic motion is doubled. Which of the following quantities doesn't change? So when I approach this problem, it's more like, okay, I have to figure out which ones do change, right? And then work backwards from there. So talk me through it. How did you reason through this? Or you just picked one? A, B, C, or D, it has to be something. Not E. How did you start? How did you start? Go for it.
We said it wasn't A
Why not?
because the energy would increase because the height or displacement in this case would be greater.
Okay, so the energy is going to go up because the displacement goes up. And can you use even maybe a formula or an equation to like show that that's going to be the case?
Mass times what would be gravity, but it'd be acceleration. Mass times acceleration times the height. The mass and the acceleration are gonna stay the same, I guess. Well, at least the height's changing. That's all we know. So.
Oh, is that like potential energy?
What kind of potential energy are we talking about? Maybe let's talk about it in this way. Is that okay?
Yeah.
I mean, I think your reasoning works also, but it seems a little less intuitive to me.
Yeah.
If we take gravity out of the problem when we do it this way, if we increase the amplitude, that's increasing. What is gravitational, or not gravitational, excuse me, spring potential energy equal to?
1/2 kx squared.
Is that okay? So the maximum is going to be 1/2 k times a squared. Is that okay? And you may, I mean, like that's not something that's really deep, dark secret, but it's kind of important. So I don't know if you want to write that down or not. But anyway, if the amplitude gets bigger, what's going to happen to the maximum energy? Bigger. It's got to get bigger. Okay, so A is out. Help me out. What else can I get rid of? One down. I need to get rid of 2 more to feel confident. You all wrote answers down, and the answers weren't not A. What else can you get rid of? Go well, and then we'll go over here.
Maximum speed changes because if you have like a spring on a mass, then the longer that it's accelerating downward, the higher the speed will be.
The longer it's accelerating downward, the higher the speed will be? Sure. Where does it have a maximum speed, by the way? At equilibrium, does that make sense? So that's at the same place every time. I mean, I agree with you, but again, I kind of feel like I want to make sure that the reasoning that you're using is really solid so that it's not just conveniently the case, but it's actually the case. So if I move this over further, how can you show me that the speed, I agree, speed is not the right answer, right? We need to get rid of it. How do we know? I don't know, go.
Okay, because the potential energy you have, when it reaches the equilibrium, it will all be changed to kinetic energy. And so then you can use the same argument.
Does that make sense? So at the maximum displacement, that's going to be 0. And at the equilibrium, that's going to be 0. And so if this gets bigger, then that's got to get bigger, and then the velocity's got to get bigger too. Yeah. Yeah. All right, 2 down, 1 to go. Who can make an argument for me about either one of those two, either C or D? Jonathan?
D, even though I just realized that I got this problem wrong. But period will change just because, so the farther, because it will require more time to cross the distance. So if you change, amplitude will be representing the distance it has to travel. I think you have it in terms of a position versus time graph.
Okay, but it's not linear, is it? I don't know.
It's not linear, but it's a sine. It's either a sine or cosine wave. I don't know which. But even so, as you change, but if you increase the distance, so it's going to take it longer to go around the circle, so to speak. If you think of it, since it would look like a sine or cosine.
You're pushing hard, and I'm not sure if you're...
I'm making an analogy, and I'm not sure it's getting through.
It's not working for me. I mean, I'm not saying you're right or wrong. I'm just saying I'm not quite understanding what you're saying. Have we talked about period yet? In terms of this stuff?
I don't think you have.
I haven't. Have you? Maybe we defined period, so we know what it means.
Yeah.
So it might be period that doesn't change. It might be period that does change.
I think period changes.
Do we know anything about acceleration?
Oh, I was just gonna say that the period doesn't have to change because if we're saying that the maximum speed changes, then it would still be able to finish the full period cycle, in the same amount of time.
Okay.
Or even with
It might be able to, right? There's potential for that. Does that reasoning make sense to you, what she's saying?
Yeah, it makes sense. I'm just looking at the equation.
Cora?
Well, I was gonna say you can draw a picture and show how you have one wave, then you can make another one that has twice the amplitude and still goes through the same thing. So nothing.
So we don't know for sure?
No,
Is that what?
you can draw a picture and see that it's possible.
So you can have two. Okay, let me see if I'm understanding what you're saying. You can have a sine wave that looks like this. Is this what you're saying? And then I can have another sine wave that goes like this. Except that's really a bad sine wave, but you get the idea. Is that kind of what you mean?
Yeah. So like it has the same period.
Okay.
But
Okay.
it's twice the amplitude.
Okay. So this is evidence that it could work. We don't know for sure, right? Okay. So we've narrowed it down to 2. We've made arguments that D could be the one or could not. We're not really sure. Can anybody make an argument for C that yes, it does change or yes, it doesn't change? Go.
Okay, so the acceleration due to gravity is always the same.
Okay.
So that means that the acceleration to the spring must also be the same because the displacement is proportional to the or displacement from equilibrium is force versus net force. So it means that acceleration has to be like consistent.
Okay. So I'm gonna ask you two questions. And it doesn't. Will doesn't have to answer these, but I want everybody to kind of help think so that you can know the answer. Is the acceleration of the spring the same the whole time as it's bouncing up and down? Is the acceleration constant? The acceleration due to gravity is constant.
Yeah.
I agree with that. But is there a net force acting on this object?
Yes.
If there's a net force, that means it's accelerating, right? But is it moving every moment?
No.
What about this part right down here? It's not moving, right? If it's not moving, that means its velocity is 0, right? So that means we've got some sort of change that it's moving at a maximum speed, and then it slows down again. You see what I'm saying? So I don't think the acceleration is constant, even if we just watch this happen. What if we take this one, where it's going horizontally? Is gravity acting on this spring? Or on this mass, excuse me? Yeah. What else is acting on the mass? The normal force. And how do the gravitational and normal forces compare?
Equal.
They're equal in magnitude, right? Are there any forces acting in the x direction? The what?
Spring force.
The spring force. And is that spring force causing an acceleration? It is. It is. This is the suggestion that I would make. Hey, we wrote it down before. What's F net? F net is equal to, in this case here, where's the F net pulling or pushing? Or what F net is pulling or pushing? What is pulling or pushing on it? The spring, right? Is that causing an acceleration? Yes. What's that acceleration equal to, Emily? Or how can I express that acceleration on this statement? What could I write there?
The K.
Mm-hmm. Is that okay? If I increase the amplitude, what am I changing here?
Distance.
This guy here, right? If I change this, have I changed the K value?
No.
Have I changed the mass? So have I changed the amplitude?
Yes.
Yes. Yes. So the maximum acceleration does change. By process of elimination, we can say that this guy doesn't change, and we're going to show that that's true. We're going to start that process today. We'll get there on Wednesday. Okay?
How I did get that right then?
All right. On your paper right now, I've got a picture that I want you to draw on your paper. This is one of those, like I actually do want you to put it on your paper so that you have it to refer to when you're looking back and studying and trying to get a handle on what in the world's going on here. I've got another horizontal spring. They didn't draw a floor on each of these, but it's not going to like do a pendulum craziness, okay? It's flat out this way. So gravity doesn't matter. Does that make sense? The only thing that's acting, that's causing any acceleration is the spring force. I'm going to label these just so we've got things to talk about officially. Oops, I don't want that. I want this. Oh, hello. Go away. Sorry, there we go. I'm going to call this one A, B, C, D, and E. I'm going to give you a moment just to draw that picture. It doesn't have to be perfect, but to get a sense. Let me show you also that this is labeled negative A for amplitude. That's the 0 position, so that's equilibrium. And here's positive A for amplitude. Go ahead and draw those pictures for me. And once you've done that, your task is to identify displacement, velocity, acceleration, and net force at each of those places as either a max, a min, a 0, or none of the above. Okay? So you may want to make a couple columns, right? Like a displacement, velocity, acceleration, and force column. And I want to know at each of these places, each of these 5 spots, are they at a maximum, minimum, a 0, or does that not make sense for that place? Okay? I'm going to give you just a couple minutes to take a look at that.